Ready? Okay, so thank you very much for organizing this conference, specifically after the last break night, which I really enjoyed. Now, possibly it's my turn to entertain you with some physics. I mean, if you don't get entertained, then that would mean that I'm still at the zone. So, pardon me. Okay, so on a serious note, I'll be talking about how to probe leptogenesis with gravitational waves. And the material I will present in this talk done with in collaboration with these guys, where Pasquale Di Bari is in Southampton, Satabrata and Ambor Ghoshal, they work in India. Sabiri is here, who gave a talk yesterday, and Federico is my colleague supervisor. Okay, so this is the subject line of the talk. How to probe high-scale leptogenesis with gravitational waves. High scale, by high scale I mean the scale which is not accessible by the collider, and typically it's like about TV scale or something like that. So the basic idea of my talk is to connect cosmic strings with leptogenesis. Like leptogenesis are typically related to some heavy particles in your theory. For example, if you do seesaw, it's related to the mass of the heavy neutrinos. And what I'm claiming that if you generate the mass of the heavy neutrinos, say for example, in U1 symmetry breaking, you can have cosmic strings. And the fun fact with cosmic string is the amplitude of the gravitational wave you get is typically proportional to vacuum expectation value of the UN scalar you introduce in your theory. So if the symmetry breaking scale increases, that means the amplitude of the gravitational wave increases, and therefore I think this cosmic string stuff are very good probe of high scale leptogenesis, which is otherwise not accessible at the colliders. So this is the basic idea of the talk, and I'm working on this topic since the last year actually. Okay, so you already heard many talks on leptogenesis. Just to have a brief summary. In seesaw, once you include this right-handed neutrino fields along with the standard model particle content, you can write this Dirac mass term and this Majorana mass term. With these two kind of mass term, you can generate light neutrino mass. But the main point is, if you include this Majorana mass term or heavy neutrinos, they can decay CP asymmetrically to lepton and Higgs, or anti-lepton and anti-Higgs, like the CP conjugate state of Higgs. And if there is a CP violation in the theory, or if the Yuka couplings are generically complex, then there could be a mismatch and you generate lepton asymmetry, and those lepton asymmetry will be further converted to baryon asymmetry via Fallerian transition, and therefore you we can explain the observed baryon asymmetry. So this is the basic idea. And the thing is, so this is a bare mass term of the right-handed neutrinos. Now we can generate this mass term with a dynamical symmetry breakings, for example, with an UB minus L. Okay, so far the test, there are numerous number of work to test leptogenesis as collider. These are the papers which I like the most. For example, the heavy neutrino oscillation. In this case, you can probe the right-handed neutrino mass scale at GeV, and resonant leptogenesis, which was one of the seminal paper in this direction by Apostolos, who is here. And also leptogenesis with Higgs decay. But all these, most of them assume that the right-handed neutrinos you include in your theory are quasi-degenerate, and therefore they are accessible to the colliders. And indirect test, you can also test leptogenesis indirectly. For example, in general, if in general leptogenesis mechanism is not sensitive to neutrino mixing parameters. To get it sensitive to neutrino mixing parameters, you need to include effects like flavor effects. So what is flavor effects? A brief summary is you have this heavy particles right-handed neutrinos that decay to lepton states and Higgs, and at a certain point of time, these lepton states and Higgs will reproduce the right-handed neutrinos, which are called inverse decays, and typically it washes out some sort of asymmetry, and finally you get what you get. But the point is, since these are lepton states, they can interact with the right-handed charged leptons, and therefore, and initially you produce these states as a coherence states, and once they interact with these coherent states, these charged leptons, right-handed charged lepton fields, it typically breaks the coherence of the system, and this I state basically can be split into two states, beta or gamma. And at the point of inverse decay, instead of I, this beta and gamma basically interact and reproduce the right-handed neutrino or give the washout effect. So once you include flavor effect in leptogenesis, basically there are two kinds of effects you include in a theory. Firstly, you relate the CP asymmetry parameter, which is responsible for generating lepton asymmetry, is basically you can relate that CP asymmetry parameter with neutrino mixing. And also the inclusion of flavor effects, they basically reduce the washout effect. So, in this way you can generate you can relate the lepton asymmetry to neutrino mixing parameters indirectly, and therefore you can test leptogenesis indirectly. A prototype example which I did last year with Pasquale Di Bari in Southampton. So it's a kind of high resolution simulation, Monte Carlo simulation of leptogenesis in SO10, where you assume the Dirac type mass metrics are similar to the quark mass matrix, and this is a 3D parameter space of leptogenesis in SO10 or SO10 inspired models, where in this axis you have the delta, which is the Dirac CP phase, which you measure in the experiments. This one is the theta 23, is the 2-3 mixing angles of the neutrinos, and here it's the in z-axis it's the lightest neutrino mass. So the takeaway point is, if you at the best fit values, see this red line is the best fit values, you have a lower bound on the lightest neutrino mass, and accordingly you can have a lower bound on neutronless double beta decay. Therefore, finding signals at neutronless double beta decay, you can falsify this kind of scenarios like leptogenesis in SO10. So this was the indirect test. Now I will go to the gravitational waves. I mean, the things which motivates me to do this kind of to connect leptogenesis with gravitational waves are the pulsar timing arrays. So pulsar timing arrays basically detect signals from the pulsars. So pulsars are highly magnetized neutron star. They basically emit pulses, and due to the high density of the neutron star, you get very precise and frequent pulses at the Earth. And if some kind of disturbance like gravitational waves passes through this Earth and pulsar system, you can find that distortion in a mathematical quantity or the measurable quantity called time residual at the Earth, and therefore you can infer that whether there could be gravitational waves or not. And the recent finding of a detector called NanoGrav in US, they claim that they have found like evidence for a stochastic common spectrum process across 45 pulsars that could be interpreted as gravitational wave, but there are certain characteristics it has to satisfy. So it's kind of ambiguous right now whether it's a stochastic gravitational wave or not. But if it's a gravitational wave, that would mean a lot, because in general the pulsars work with high amplitude gravitational waves, and if you deal with cosmic strings, those high amplitude gravitational waves typically link to high scale symmetry breaking, and therefore you can probe theories like grand unification and leptogenesis and whatever you want. So I did some stuff with leptogenesis I'm gonna show. Okay, so cosmic strings. I'm not going into detail of the theories portion. I'll just try to show the results and basic idea. So the cosmic strings are typically related to symmetry breaking, like U1, which was first introduced by Kidley. And once the strings are formed, they can intersect and form closed loops, and they can shrink via gravitational wave emission. So still there are debates whether they lose energy particles or via gravitational radiation. But recent simulation based on number-go actions shows that which can typically be satisfied at our universe. That the dominant emission is gravitational waves if the symmetry is local gauge symmetry. For example, in seesaw you can put this local gauge symmetry as UB minus L. So typically these cosmic strings radiate gravitational waves at a constant rate, and this is the loop length dynamics. You produce an initial loop of size alpha Ti, where Ti is the cosmic time or the horizon size, and this is the effect that you introduce with the gravitational wave emission, and the loop shrinks via gravitational wave emission. And the recent numerical simulation finds that this alpha should be very large in order to produce significant amount of gravitational wave. But the main point is the amplitude of the gravitational waves is proportional to the square of the symmetry breaking scale. Again, I'm repeating it because I want to probe high scale theories. So this is the typical formula for gravitational waves that you can find in many places, and this is the differential energy density of gravitational waves, which is related to power spectrum of gravitational waves, which can be computed precisely analytically in flat space time actually. But the point is, it's proportional to mu square, where mu is the string tension and related to vacuum expectation value of the E1 field. And the most important part for this one to compute this gravitational wave loop for loop number density that would contribute to the gravitational waves. This is a kind of numerical formula which are obtained in radiation domination. And if you put these things, this loop number density in this expression, you can find the frequency and amplitude dependence of gravitational wave. So okay, so please don't take this plot seriously because I generated these plots with my hand. So basically, you can relate the high scale physics with with gravitational wave amplitude, gravitational wave spectral shapes. So what do I mean by gravitational wave amplitude? It's like if you are in the standard cosmology, the typical cosmic string spectrum are flat at higher frequency. So if you have a symmetry breaking at let's say of the order of 10 to the 15 GeV, you can have gravitational wave signal at pulsar timing arrays, laser, as well as advanced LIGO. So this way you relate the amplitude of the gravitational waves to the high scale physics. But you can also play with the spectral shape. So if you put a matter domination before a radiation domination, which is allowed basically, and this spectral shape basically falls. This spectrum basically falls. And if you have scenarios like kination, this amplitude increases at a certain point of frequency. So we call it turning point frequency. So looking at this turning point frequency in several gravitational wave detectors, you can basically probe leptogenesis. So I wrote 3 papers in these three categories, where in the standard radiation domination, there are 2 papers right now. Well, one is by Murayama, one is by me, Murayama et al., and one is by me. And then in these 2 category, I wrote this paper, Leptogenesis from Primordial black holes, where primordial black holes can dominate the energy density of the universe and act as a matter, and therefore it changes the spectral shape of the gravitational waves generated from cosmic string. And this one is a gravitational leptogenesis, where kination-like scenarios are natural call for this kind of scenarios, where you have a spectrum like f to the 1 after this turning point frequency. Okay, so before I go to the discussion about those scenarios, let us show me some non-standard spectrum. For example, this is the standard spectrum in radiation domination, but if the symmetry breaking happens during inflation, there could be dilution in the loop number density, and you can have spectrum like this, which are non-flat. And we recently probed these kind of scenarios, which are melting string, which is, with Sabir is here, where the vacuum expectation value is temperature dependent, typically goes as T² basically, and therefore you basically change the spectral shape. The spectral shape is not flat. So these are some sort of non-standard spectrum. Now I will come to gravitational leptogenesis. So the basic idea behind gravitational leptogenesis is that if you have an operator like this, del mu r j mu over m square, where r is the Ricci scalar, it corresponds to a chemical potential which is proportional to r dot, and it can be generated in seesaw model basically at 2 loop. So so basically, once you have chemical potential in your theory, you can generate lepton asymmetry in equilibrium, which in general you cannot. But so this is a kind of dynamics. This is the equation which governs the evolution of the asymmetry, where the delta L equals to 2 process in CISO models try to keep the lepton asymmetry in equilibrium, and once it goes below the Hubble expansion, the asymmetry freezes out. It's like similar to the freeze out of dark matter, and at a scale of the lightest right-handed neutrino, you can have another washout, and finally you get what you get to make it successful. But the main point is this equilibrium asymmetry, and therefore the final asymmetry is proportional to 1 minus 3 omega, where omega is the equation of state. If you are strictly in the radiation domination, you can compute the thermodynamic potential at high temperature using the, let's say, standard model QCD potential, but you cannot generate significant non-zero value of 1 minus 3 omega with standard radiation domination. Therefore, a non-standard cosmology is a natural call for this kind of scenarios. And if you can put omega equals to 0, for example, a matter domination here, but you can show that if you put omega equals to 0, these kind of mechanisms are not very effective, and it's sufficiently dilute the final asymmetry. And as I said, for this kind of leptogenesis scenario, you can have this gravitational wave spectrum, where this red line is ruled out by Babian, and this blue line is kind of allowed spectrum. You can also connect this leptogenesis to low energy neutrino variables. For example, this is a plot of NB minus L for the final asymmetry with M1, and if a curve like this cuts this horizontal white line in this green space, so in this green region is the sensitivity region of current neutronless double beta decay experiment. That means you have a test for that neutronless double beta decay experiment, and you can show that if this curve cuts at this horizontal line, that is, that you can do it only for a set of values of G mu and T star, where the T star is the temperature to which the non-standard epoch acts, and this is the current sensitivity limits of various gravitational wave detector. This portion of the parameter space is ruled out by Babian, and this portion of parameter space is ruled out by the particle production due to the smaller size of loop. So this is a kind of allowed parameter space for this kind of scenarios. But the main point is, if you increase the amplitude of gravitational waves, then the spectral break or the T star shifts to the right side, and therefore you can make predictions from predictions in gravitational wave experiments. So this is the scenario of matter domination, where we consider ion symmetry breaking before, where you consider a scenario like black hole formation and ion symmetry breaking before black hole formation, and those right-handed neutrinos are getting produced by Hawking radiation. So the point is, these are some key formulas you can look at, but the key point is, if you produce black holes in the early universe, they can dominate. So this is the mass versus beta plot, where beta is the initial energy density of the black holes compared to the radiation. And for certain values of mass, you can have black hole domination and radiation domination. And if black hole dominate, that can act as matter. Therefore, they basically change the spectral shape of the gravitational waves rising from cosmic rays. So this is a typical. Okay, so let me explain this line. So if you have 10 to the 15 gram black hole, they can act as a dark matter. There are several papers on this side, but this side is typically unconstant. I mean, the initial fraction is unconstant, and therefore you can do a lot of particle physics here. I mean, for this low mass with this low mass black holes. So as you can see from this picture, that if you increase the beta or initial fraction of the energy density of black holes, it can dominate the energy density of the universe for a significant period of time. If you lower the value of beta, let's say if you do 10 to the minus 7 or something like that, it doesn't dominate. So this plots are generated for 10 gram black hole, I suppose. And also, if these black holes dominate, they can produce significant entropy, and therefore any thermal production or any thermal relic will be significantly diluted. For example, if you want to consider thermal leptogenesis in this scenario, you can show that the final asymmetry is diluted by black holes. So whatever you get only from the right-handed neutron production from black holes. So this is a typical allowed parameter space for black holes, where only 10 to the 13 black hole mass less than 10 to the 13 gram can generate correct baryon asymmetry, and the corresponding gravitational wave amplitude I showed in this plot. It's really at the level of LIGO and passes through nanogram for 3 benchmark points. So the point I'm trying to make is is that gravitational waves from cosmic strings are really very nice probe to for the scenarios like leptogenesis and grand unified theories. There are recently there are 2 papers on grand unified theories by Steve King, I guess. They also did similar kind of stuff. And this is a future improvement that I want to consider. For example, in this black hole leptogenesis scenario, I'm almost done. We didn't consider any black hole string network formation. I mean, that can potentially affect the spectrum. For example, one can form binaries of black hole when the cosmic strings are attached to 2 black holes, and that can change the spectral shape of the spectrum. So I'm kind of, I mean, to be honest, I don't understand the theoretical aspects of this scenario, so I'm kind of studying it. And we are also accommodating, trying to accommodate a super heavy dark matter from black holes along with leptogenesis. And so we name this dark matter as black rhinos. Rhino is an abbreviation for right-handed neutrinos, so which could be probed by gravitational waves as well as cosmic rays. So this is the summary. Gravitational waves could be potential probe of high-scale leptogenesis, which otherwise cannot be probed in colliders. Towards a clean probe, one may relate the spectral shape of the gravitational waves to leptogenesis along with the gravitational wave amplitude. And I discussed 2 concrete models for 2 types of leptogenesis scenarios. One is gravitational leptogenesis that gives a rising GW spectrum after the turning point frequency, and one is leptogenesis from black hole via Hawking radiation, which corresponds to a falling gravitational wave spectrum. Thank you.
Thank you for this interesting talk. Are there any questions?
Yes.
What sort of signal will you see in the gravitational wave detector when you observe these?
What sort of signal?
Yes. What sort? Is it? I mean, because we have events in.
Yeah, sure. I mean,
here, if I understand correctly.
Yeah.
You have continuous, but that looks very questionable.
Yeah, of course. I mean, cosmic strings spectrums are kind of flat, and therefore, it doesn't depend. It's not a power law signal. I mean, most of the gravitational wave detectors are, integrated to a power law sensitivity. So basically, it corresponds to gamma equals to 0 or something like that. I mean, if you parameterize these gravitational waves as if to the gamma, the cosmic string corresponds to gamma equals to 0 at high frequency. So basically, you need to do some Bayesian analysis and try to see which gamma is corresponds to. I mean, which gamma is close to 0. I mean, that's the same percent. For example, this the recent nanograms, they did this power law fit to the gravitational wave spectrum, and that they produce a contour of gamma and spectral index. So this kind of parameterizing the gravitational wave as a power law, you can basically do a simple fit.
Okay, so this black hole leptogenesis,
right.
It appears that the mechanism is that you have the black holes that produce right-handed neutrinos.
Yes.
Right, and then you have standard leptogenesis from the decays.
Yes.
Is that right? So it's not
exactly.
a new.
Exactly.
So let me come to the other one, to the gravitational leptogenesis, which looks that you have a different dependence on the neutrino mass. They have a neutrino mass. I don't know, somewhere you have a formula.
Yes. Okay, let me.
I think you passed. Okay, that's fine. And of course, it differs from the standard one or from the resonant one, but that when the 2 heavy neutrinos become degenerate, this goes exactly to 0, right?
Yes.
That's the point.
Yeah.
Of course, this is obvious in the previous case because we have this Yasko type or whatever, this CPO triphasic invariant, which I mean, many other people also happen to work and connect with the leptogenesis, and you understand that.
Yeah.
Here, however, you can see is that when you have hierarchical neutrinos, that's not a problem that you get symmetries. When you are even go to the massless limit, you have a singularity. You hit a singularity.
Yeah.
This question you might not ask to you, ask also to Jamie McDonald, but I didn't want to see any answer. I don't know if you have an answer to this problem.
No, not really. To be honest, no.
Okay, so it's a question.
Yeah.
Any more questions, comments? So actually, I have one. So you said that the amplitude of the gravitational waves is proportional to the depth of symmetry breaking scale.
Yeah, I mean square of the symmetry.
Yeah, but I mean, so can you like give some estimate for like some upper bound on the leptogenesis scale?
Yeah, for example, if you are in the standard seesaw, you can bound the right-handed neutrino from above with the seesaw perturbativity condition, which is typically below the planification scale, like 10 to the 15 or 5 times 10 to the 15 GeV. If you use the current Newton oscillation data along with the perturbativity condition, so that would correspond to a signal like here. I mean, at the level of pulsar timing arrays and like
for 10 to 15.
10 to the 15.
Okay. And the other question, so suppose we see a signal. I mean, is there any possible way to somehow distinguish whether those strings are related to leptogenesis or with other like Q1 breaking?
Yeah, I know. That's why I tried to give this complementary prediction on the neutronless double beta decay experiment.
Okay.
So you test in both this kind of scenarios in both the ways, actually.
Okay, thank you. Any more questions? If not, let's thank the speaker again. Okay. So the next speaker is Athanasios Bakopoulos. And Athanasios will talk about black hole and wormhole solutions in Hrondevsky theories. Or maybe even more about wormhole solutions. Is it already online? Okay, so please start.
Can you hear me? Okay. First of all, I would like to thank the organizers for giving for giving me the opportunity to present my work here. Okay. My name is Athanasios Bakopoulos, and today I will present you our recent work about wormhole solutions in beyond Hrondevsky theories. The outline of the talk is as follows. At first, I will give you a short introduction about wormholes in general relativity. Then I will move to the scalar tensor theories, and finally I will present you one wormhole solution beyond Hrondevsky theory. In this talk, I will give you some unpublished results from our recent work. So I will present you one beyond Hrondevsky solution, but I will not go into details about its derivation. And this work has been made in collaboration with Panagiotis Kadi and Christos Harmousis. A wormhole is a solution of the Einstein field equations, which has the property to connect two distant regions in space-time. A wormhole may connect two distant regions of our universe or two different universes. However, the difference between the two kinds of wormholes is topological, and an observer who makes measurements near the wormhole cannot identify its class. The first wormhole solution, which is known as Einstein-Rosen bridge, was found by Einstein and Rosen. This solution was constructed as a geometrical model for elementary particles. The solution may be easily constructed from the Schwarzschild black hole by making these coordinate chains. And the solution has this form now. And here, the circumferential radius, which is the coefficient in front of the angular part of the metric, has a minimum at u equals to 0, where the radius is the Schwarzschild radius. And this is the definition of the throat. However, the new coordinate is a bad coordinate, which covers only a part of the black hole geometry. The transformation discards the interior region of the black hole and double covers the exterior region. The Einstein-Rosen bridge is not an actual wormhole, but rather a disguised black hole. And there are some big problems with this kind of wormholes. Einstein-Rosen bridges are one-way wormholes. And this is because the horizon is a one-way surface. The wormholes have an entrance, black hole horizon, and an exit, a white hole horizon. But we know that white holes are unnatural and unstable objects that do not exist in our universe. So these wormholes have an entrance and no exit. And a particle that crosses the throat or the horizon is trapped inside the black hole. Another problem is that the huge tidal forces near the throat or the horizon would rip apart the traveler before he reaches the throat. Finally, the interior of the black hole is dynamic, and the throat of these wormholes opens and closes so fast that even a photon cannot cross it. Another interesting solution is the Geon. The Geon is a solution of the Einstein-Maxwell coupled system and was found by Wheeler. The metric for these solutions is everywhere flat except of two widely separated regions which are connected with a wormhole-like structure. Today, we could say that the Geon is an unstable gravitational electromagnetic quasi-soliton. They were also constructed as models for electrical charges and particle-like entities. The main problem with these solutions, except of their stability, of course, is their size. The typical size for a Geon is of the order of the Planck length. The modern wormhole physics started with work written by Morris and Thorne. And in this, they suggest that we may construct traversable wormholes using an engineering-like technique. We start with a metric which describes a traversable wormhole, and by solving the Einstein field equations in the reverse direction, we find the associated energy-momentum tensor. Now, if we know the form of the matter distribution which supports the solution, we theoretically may build the wormhole, or more realistic, to search in the universe in order to detect an astrophysical wormhole. But how can we construct these solutions? We start with a metric like this one, a spherical symmetric line element, which should obey everywhere the Einstein equations. First, the wormhole must have a throat. And therefore, this quantity here must have at least one root. Then there must be no horizons. So the other metric function must be everywhere finite. Finally, there must be no space-time singularities. So all the scalar quantities must be everywhere finite. In this system, the radial coordinate covers only a half of the wormhole space-time. So in order to find the solution in both asymptotic regions, we use this transformation here. The metric has this form, and now the new metric functions are everywhere finite. Morris and Thorne have also imposed some constraints in order to make the wormhole traversable by humans. We may adjust the parameters of our solution in order for a traveler to feel acceleration compared to Earth's gravity acceleration and small tidal forces. And also a traveler should be able to cross the wormhole in a finite and small proper time. And Morris and Thorne suggest less than a year. Of course, an astrophysical wormhole may not respect these constraints. Also, the solutions should be stable under perturbations. The last step is to find the associated energy momentum tensor and build the wormhole. So, have we managed to construct a physically accepted solution? Well, traversable wormhole in the framework of general relativity violates always the energy conditions near the throat. So, we need exotic matter in order to keep the throat open. In scalar tensor theories, we may also derive solutions for wormholes. In this case, we may find solutions with a traditional method by solving the differential field equations. However, we usually need phantom scalar fields. The most characteristic example is the Ellis-Bronikov wormhole, which is described by this solution. And note here that we have the opposite sign in front of the kinetic term, and therefore this field is a phantom one. Another interesting case is the Einstein scalar Gasbone theory. This theory has the correct sign in front of the kinetic term and a non-minimal coupling between the scalar field and the gravitational field through the gravitational Gauss-Bonnet term. These are the equations of motion, and here T mu is the effective energy momentum tensor due to the scalar field. So the first realistic wormhole solutions in 4 dimensions was found by Candé, Clayhouse, and Kunz in the Einstein scalar Gauss-Bonnet theory with an exponential coupling. They used the Dilaton field. They used this metric here, and they found regular traversable wormholes which do not need phantom fields or exotic matter. 2 years ago, with my collaborators, Adoniou, Candé, Clayhouse, and Kunz, we found that the Einstein scalar Gauss-Bonnet theory accepts wormhole solutions for any form of the coupling function. And also these solutions may have a new feature, a double throat topology. We used this metric, and now the circumferential radius may have a minimum, which leads to a single throat solution, or a local maximum and a minimum, which leads to a double throat solution. For a spherically symmetric space-time, the null energy condition has this form. Using our metric, we find this equation here, and since there is a minimum at the throat, the null energy condition is always violated. However, this violation is not attributed to the presence of a phantom field. The Gauss-Bonnet term generates a negative effective energy density which violates the energy conditions. This is a purely gravitational effect that has nothing to do with exotic matter. In order to find the solutions, we start from the 2 asymptotic regions. We assume that there is an extremum on theta equal to 0. This will be a throat or an equator. And we find that the solutions there have a polynomial form. And the condition for the extremum requires that this coefficient here is 0. In the other asymptotic region, we find that the solutions are asymptotically flat. So for any form of the coupling function, we may construct both a regular throat or equator and an asymptotically flat region. The solution between may be found using numerical integration, where we use these two solutions as boundary conditions. In the first plot here, we have some solutions for exponential and polynomial coupling functions. In these two plots here, we have the domain of existence for the exponential and the quadratic coupling functions. The black line at the bottom have the Gasbone black holes. Colored solid lines have the double throat solutions, while the dashed lines have the single throat. And this is how a double throat solution wormhole looks like. We have the two minima, the two throats, and a maximum in between, which is the equator. So far, we have discussed what happens in the half of the wormhole spacetime. If we want to find the solution in the other half of the wormhole, we have two ways. First, we may start with the same initial conditions at theta equals to 0 and integrate up to minus infinity. Or we may impose Z2 symmetry. In the first case, we find singular solutions, so we impose the Z2 symmetry, but now the solutions are not continuous at the throat. So we have to, I'm sorry, are not continuous at theta equals to 0. This might be a throat or an equator. So we have to place a thin shell of matter around this region and impose junction conditions. We may simplify our analysis by assuming that the matter is dust, and we find that its energy density is real, therefore it is ordinary matter. So, to conclude, the Gasbone wormholes do not need phantom fields or exotic matter. Despite of their good characteristics, there are indications that these wormholes are unstable. Actually, there are indications that every wormhole in Hordensky theory is unstable. There are some no-go theorems. On the other hand, there are works which indicate that wormholes may be stable in the beyond Hordensky theories. So, in our recent work, we seek for wormhole solutions in the framework of the beyond Hordensky theory. We use the shift-symmetric beyond Hordensky theory, where the two beyond Hordensky coupling functions are not independent since we impose this generacy condition. We use a spherically symmetric form for the space-time, and we find the solution here, where the nature of the compact object is determined from the roots of the metric functions. We start with the GRR metric function, and this equation here is equivalent with this one. This is the definition of the lambda parameter. And now we have two cases. First, if lambda is equal to 1, the two metric functions have a common root, and therefore the compact object is a black hole. But if lambda takes values in this regime, the metric function f has a root in a point where h is finite, and therefore the compact object is a wormhole. From the expansion at infinity, we find that The space-time is asymptotically flat. I remind you that in this coordinate system, the coordinate arc covers only half of the wormhole space-time, so we use a different coordinate system, and the numeric functions are everywhere finite here. And this is the theory which supports our solution. In the first plots here, we have the metric functions for wormhole solutions with lambda equals to 0.2 and 5 different values for the coupling constant alpha. In the third plot, we have the scalar field for these solutions, which has been found numerically. We observe here that the solutions are everywhere regular, and they are also continuous at the throat. The same happens for the first and second derivatives. So, in this case, we do not have to place a thin shell of matter around the throat. The null energy condition has this form, and in this plot, we have a null energy condition for these solutions. Again, it is violated at the throat, but again, this violation is not attributed to the presence of a phantom field. It is just a characteristic of our theory. In these plots here, we have the domain of existence with for the wormhole solutions with lambda equal to 0.2. In the first two plots, we have the values of the null energy condition at the throat. In the third plot, we have the H scalar at the throat, while in the last plot, we have the values of the energy, effective energy density at the throat. We observe that the null energy condition is always violated at the throat for every wormhole solution. And the wormhole solutions maybe have positive or negative values at the throat for the Ricci scalar and the effective energy density. Morris and Thorne have considered wormhole solutions with positive or negative values for the energy density. However, in their case, the solutions with energy, with positive energy, had the exotic matter stretching all over the space-time. Trying to localize it, they were forced to consider only solutions with a negative energy density at the throat. Here, we indicate 6 wormhole solutions with red dots, and we plot them. We observe that they are everywhere regular, and from these two plots, we observe that they are localized around the throat independently of the sign of the Ricci scalar. Sum up. Sorry. A very useful way to visualize the geometry of a given manifold is the construction of the corresponding embedding diagram. Since the solutions are static and spherically symmetric, we may simplify the analysis by choosing constant values for the t and theta coordinates. And this is the embedding diagram for the previous solutions, where the 3D plot corresponds to the solution, the first solution with the blue line. Sum up, regular analytic wormhole solutions were found for a class of the beyond Kordensky theories. The profile for the scalar field in all of the cases considered was found to be regular over the entire radial domain. The solutions are traversable and do not need phantom field or exotic matter. The solutions are continuous at the throat and they do not need a thin shell of matter. And finally, for every wormhole solution, the domain of existence was found. Thank you.
Thank you very much for interesting talk. Questions? Sure.
Yeah. My name is Apostolos Pilaxis for the online attendees. Right. So I'd like to clarify one thing. I don't know if there's a question. So in the first part, non-Hortensky theories, so you have added a Gasbone term coupled to a function.
Here.
Okay. So you coupled and also had the correct metric for the 5 field. So you have, why you say you don't need? I mean, you need the F of 5. Why you say you don't need the ghost? Sorry, you don't need the matter. You need the matter, not exotic matter, but you need some matter.
Yeah, we do not need the matter in order to derive the solutions. We need matter because we impose this Z2 symmetry here. We need matter because the solutions are not continuous.
You need an F of I, right? You need an F of I.
Yeah, we need an F of I, but we also need to add matter here. But this matter is also ordinary matter.
Yeah, I see. It's could be. Of course, one could see whether. Yeah, I guess that the quantum effects. What happens, but you already have a kinetic term, which is well defined. Okay, thank you.
We have also online question.
Yes.
So please.
Can I ask it, the online?
Yes, please.
Okay, thank you. Very nice talk. I would like to ask again about this matter. So your matter is necessary because of what? I mean, you could have traversable wormholes with just the Gasbone and the scalar field. Am I right?
Could you repeat the question?
Oh, sorry, yeah. When you say you had matter, extra matter, what did you mean other than the scalar field?
Yeah.
So if you have only the scalar field, let's say that the scalar field is the dilaton in string theory, you could still have traversable wormholes. That was the work by Kuntz, Jota, and am I right? Or
well, the problem is here. If we want to find continuous solutions at the throat, these solutions are singular in the other part of the wormhole.
right.
If we impose the Z2 symmetry, there is a discontinuity here. And the only way to describe this is to add some matter in the theory.
Because of the matching conditions, that's what you are saying. But does it have to be matter or it could be something else?
We have the matter here but from the junction conditions.
Yeah, but it has to be matter with positive energy. That's what you're saying.
Yeah.
Not exotic matter, ordinary matter. That's my question.
The junction conditions say because this is the density of this matter. Right. These are the junction conditions.
Okay.
This matter, the energy density depends from the parameters in the coupling function, and it happens that it is the energy density here is positive.
Okay. Thank you.
Thank you.
Thanks very much.
Thanks very much.
We still have some time for questions. So maybe I will ask, is there like any implications for cosmology of those wormhole solutions? Like for the, I don't know, for the fate of the universe?
This pattern, yeah, maybe they have some implications, but
okay, but no one has studied it yet.
I'm sure that there must be some works, but I'm not familiar with this literature. Can we say that?
Yeah, I think. Can you use the microphone?
Yeah, we haven't detected wormhole. Yes.
So I think we should thank the speaker again. And now we'll have an online talk by Jorge Alfaro.
Can you see it? Can you see it?
Not yet.
You have to make me co-host.
Yeah, now we see the slides. So the talk will be about axial anomaly in very special relativity. So please start.
Okay. Thank you very much. I want to thank the organization for the invitation to the next conference. So this will be my talk, the study of the axial anomaly in very special relativity. Yeah, this is the resume of the talk. It's a motivation that will right away. We will review the very special relativity standard model. Review also a regularization in the infrared, what is called the Mandelson-Leyland regularization, which will be needed for the computation of the anomaly. And then we will go into the main part of the talk, axial anomaly in very special relativity electrodynamics. And this talk is based on this work published this year. So, as you know, the oscillations created again a puzzle in the standard model, because it showed that some of the neutrinos must be massive. Instead, in the standard model, the neutrinos as massless and left-handed. So this means that we have to go beyond the standard model in order to incorporate neutrino oscillations. The standard, one of the standard way to do that is to use the seesaw mechanism, but that means that the introduction of more particles and in general right-handed neutrinos. And there is a different possibility that was proposed in this paper by Cohen and Glashow, which is called very special relativity. We are going to review now. Yeah. The observation is that all kinematical effects associated with the invariance under the Lorentz group with 6 parameters can be obtained from 4 parameters subgroup of the Lorentz group, which open the road to new prediction with violate Lorentz symmetry, but you preserve the symmetry under such subgroups. So very special relativity implies special relativity in the context of local quantum field theory or CP conservation. Most interesting subgroup of the Lorentz group, which has HOM2 with 3 parameters and SIM2 with 4 parameters. The main observation is that there are no invariant tensor for these cases, for these 2 subgroups. So a special relativity kinematic is preserved. For instance, P square is the only invariant the SIM2 or HOM2. As it is the same as in the Lorentz group. No non-local Lorentz symmetry breaking operator preserving either of these subgroups exist. So that means that we have to go into non-locality. This is the main ingredient of this model. And there we have the definition in certain frame of the generator of the loop, and the now T1 is kx plus y, and T2 is ky minus gx, and the generator of HOM2 are these T1, T2, kc. Kc is the boost in the c direction. SIM2 generator are 4, T1, T2, AC, and JC. And if you take a particular null vector n, this is the one there, 1, 0, 0, 1, n is invariant under T1, T2, and JC, but under the boost in the c direction generated by Kc, and transformed by a phase. That means that if you consider 2 particle momenta and consider this ratio, then this is a very special relativity invariant, but it's not a Lorentz invariant. So if you accept the non-locality, you generate more terms in particular, and that was a proposal also Cohen and Glashow, that you can introduce a mass term for the neutrino without changing chirality and without introducing extra particles. And this is the new term. This is the modified Dirac equation, where explicitly you get this null vector here. And if you take the square of this, you get the Klein-Gordon equation corresponding to a massive neutrino. And you can see that this you can preserve the chirality of the neutrino. So this opened the way to a new manner to introduce mass in the neutrino oscillations without introducing extra particles. And this is what we did in this special relativity standard model. There, and the main observation is that LHC do not see particles beyond the standard model one. Neutrinos are massless in the standard model, but in nature they are massive. Neutrino oscillation implies that. So we want to be rather conservative here and to keep the particles and symmetry of the standard model, but produce masses for neutrinos. The Vsr standard model is a simple model. It's actually the same standard model, except that we have masses for the neutrinos using Vsr. It is a normalizable and unitarity is preserved. New non-local terms that violate Lorentz invariance are able to describe in a straightforward manner the observed neutrino oscillations. And we predict new processes, such as the decay mu going to electron plus gamma, which are forbidden in the standard model. So this is more or less what we did. We did in very brief word. We have the standard gauge field for the Weinberg-Salam model before spontaneous symmetry breaking. And we introduced the leptonic Lagrangian, which also is the same kind of leptonic fields, a doublet, left-handed doublet under SU2, and three SU2 singlet are A that only contain the electron. There is no right-handed neutrino. The index A represents the different families. The index 0 denotes the fermionic field before spontaneous symmetry break. The important thing is that the electron and the neutrino form a doublet. And if I give a mass to the neutrino using very special relativity, I will also give a small mass to the electron before spontaneous symmetry break. Moreover, you can think of these masses as some matrix in the flavor sector. So if this matrix is not diagonal, you can accept a neutrino oscillation from this term in the Lagrange. And this is precisely the way the model introduces neutrino oscillation. One can compute the effect, and they are completely within the bounds of experimental searches. Now we see what is the Vsr Quantum Electrodynamics is simply to restrict the very special relativity standard model to the electron neutrino and the electron the interaction of the electron or any charged particle. So the first observation is that in this model, the electron neutrino and the electron belong to the same doublet under SU2 left. Small m is the Vsr mass for both electron and neutrino. After spontaneous symmetry breaking, the electron acquire an additional mass, that is this one, the electron Yukawa coupling, and B is the backbone expectation value of the Higgs. Then one can show that the electron mass is modified to this quantity, where this is the spontaneous symmetry breaking mass, and this is the Vsr mass. The neutrino mass is not affected by spontaneous symmetry breaking, and simply keep this. So restricting the very special relativity standard model after spontaneous symmetry breaking to the interaction between photon and electron alone, we get the Vsr QED action. At C is the electron field, and mu is the photon field. And we use the Feynman gauge in our computation. So this is the Lagrangian. This is the Lagrangian for the photon, and this is the gauge fixing. The other thing are standard, the covariant derivative, and the F mu nu for the photon field. Remember that n dot n is 0, is a null vector. Under this condition, the vector current electric charge conservation is this one here. The actual vector current is this one, but currents are conserved in the classical level. And so we are interested in computing expectation value of this current to see how they develop an anomaly at the quantum level. The one complication of this type of model, because of the non-locality, is that actually we get an infinite number of vertices, and they are obtained by expanding this operator both in the current and in the Lagrangian as a series in the photon field, and you get the infinite series there. That produce Feynman rules that I wrote some of them here. It's not important to go into details. This is the electron propagator. This is the normal vertex photon electron electron. You see that it get modified by this quantity here because in fact the current is modified, and there is also a 2 electron 2 photon vertex. There is the one correspond to the gamma phi insertion into the current, and so it's exactly this one, but time gamma phi, and so on. So as I said, there are infinite number of them. I just wrote the one that we need for the one loop computation of the anomaly. There is a second ingredient in this kind of models is that they contain infrared divergences, precisely because they are non-local. So terms like this appear in both in the propagator, and then they will go into the loops. Also in the vertices, they appear this kind of expression in momentum space. So we have to deal with these infrared divergences, and there is some arbitrariness. However, there is a preferred way to do that because it has many interesting properties. And this is the Mantis-Sullivan description. And this was developed in the context of light-cone gauge quantization for gauge theories and string theories. This is the Mandelson-Levine prescription. You introduce a new null vector, which is called n bar, that is null and also has a non-zero projection over n. I have normalized that to 1. The Mandelson-Levine has very nice properties. The poles in the P0 complex plane are situated such that the weak rotation from Euclidean to Minkowski is justified. This is important for us. It preserves naive power counting of loop integrals. If you use some other precision, for instance, principal value, you will get tetrapoles that are not there. And in gauge theories, it maintains the word identity of the gauge symmetry. This is why it is preferred compared to other scheme of infrared regularization. The original proposal generally compute particular integrals, and they also mainly compute the divergent part. There is an interesting simplification as I develop this work here, and I will explain how it can be done. Actually, there is a hidden symmetry in this regularization with integral explicitly. For instance, if you consider the following integral here, where f is an arbitrary function of p squared, the p is the integration measure in d-dimensional space, and then mu is the fixed null vector that satisfies this relation. This integral is infrared divergence as you get n dot p equal to 0. So the Mandelson-Levine is this. So to compute a mu, we have to know the specific form of f, provide a specific form by mu and mu bar, and evaluate the residuals of the poles of this expression in the P0 complex plane, which is rather formidable for arbitrary f. We will show that this can be simplified in such a way that we can get explicit form for the solution. So instead, we want to point out the following symmetry. If you scale n mu by a factor lambda, and simultaneously you scale n mu bar by the inverse of that factor lambda, which lambda different from 0 and lambda real, it preserves all the properties between n mu and n mu bar. For instance, if we start with the null vector n, the scale vector is also null. The same happens with n bar, and moreover, the normalization is preserved by the scaling. So the structure is preserved, and moreover, you realize from the Mandelstam-Leiber prescription that this factor 1 over n dot p scale as lambda to the minus 1. So now we compute a mu based on his symmetries. It is a Lorentz vector which scale under 7 as lambda to the minus 1. The only Lorentz vector we have available in this case are n mu and n mu bar. But the scaling forbids n mu bar. That is a mu should be proportional to n bar mu. And multiply by mu to find that a dot n is small a. So you can get small a as this integral, which is a normal integral. So you have evaluated the complete form of the integral independent of the value of f. And this without any effort, simply using the symmetry. Yeah. By the same token, you compute this tensor, a mu nu lambda. This is completely symmetric in mu nu lambda. So the only possible combination of the n bar and n that satisfy the scaling, that means that a mu nu lambda goes to lambda to the minus 1, a mu nu lambda is this one here, where this bracket means symmetric in all Lorentz indices. So we compute this product, which again is a normal integral, this one here, just using dimensional regularization, and that determines completely the integral. So it is this one here. This can be generalized to any kind of integral, and in particular, the one that are interesting for us when we compute the loop integrals is the one here. Yeah. So using dimensional regularization and standard definition of omega, we obtain this general integral for any a and b in the complex plane. It's a closed integral like this. So other integral can be computed derived in respect to mu, so that if you have a p mu here in the numerator, then you can obtain that simply derived in respect to mu. And so any integral you need to compute the loops can be obtained this way. So you get the closed expression just using dimensional regularization and the scale. So now let us go to compute the anomaly. I will simply show which is the simplest case, the two-dimensional anomaly, but you will see that the same argument will apply to four-dimensional or six-dimensional anomaly. So in the two-dimensional case, we compute the expectation value of the axial vector current in the background field A nu. So this quantity here, and this is the Fourier transform of the current, and we define this object here and multiply by a mu. And that a perturbation theory is obtained by the addition of this graph and this graph here. You see this is a new graph that corresponds to the new vertex where you have one axial current and a photon. So these are the equations corresponding to the two graphs. Just you use the propagator for the Vsr electron, and the Feynman rules I already derived. I will show polyvillar regularization. We can do it in dimensional regularization too. I will simply skip that part, but let me illustrate the main point. So to compute the axial anomaly, we will use polyvillar regularization and Mandelstam-Leiber prescription to the infrared divergence. This is very important. In this kind of model, because of the non-locality, you have to regularize both in the ultraviolet and infrared. And the election of the infrared regularization is important for the result. So that's why I specify Mandelstam-Leiber prescription. So you can see that then this one is logarithmically divergent, and this one is convergent using Mandelstam-Leiber, because then you can just count the number of p's in the numerator and in the denominator, because it preserves naive power counting. So it is to check that formally this identity holds, because this is simply the conservation of a charge. If in the diagram you can shift the integration variable by an arbitrary vector k. This will be true if the integral 10 will be finite, but it is not finite, so we have to regularize it. So for that, we introduce a polyvillar particle of mass m bar and define the regularized amplitude, simply subtracting the contribution of the m bar mass, which is this. So this is finite now, so the naive wire identity for charge conservation holds. For the axial wire identity, we get this expression here. And that means that the regularized axial amplitude satisfies this relation here. And since we recover the standard or the unregularized amplitude by taking the limit m bar going to infinity, the anomaly is obtained from this expression here. So the anomaly is this part, and is obtained taking the limit m going to infinity, m bar going to infinity. So we compute that. And here, actually, it is very simple to do, because we know the main property of Mantis and Lagrange that it preserves naive power counting. So we compute the anomaly.
Sorry, could you please mute the Corfu studio? I have sent the chat email because we hear an echo. Thank you. Sorry, Jorge, please go ahead.
Yes, thank you, Nick. Yeah, so then to compute the anomaly, we notice first that after computing the trace, the integral is finite. A typical term contains the vector and mu in the form I explained here. Yeah. Now we recall an important property of Mandelson-Lagrange prescription. It preserves naive power count. So according to this, for large m, this expression C mu goes as m to the -1. So it goes to 0. So following the same argument, we can easily check that all terms containing mu vanish when m goes to infinity. So only remains the Lorentz invariant term. And I compute this and get, of course, the standard Lorentz invariant result. I want to emphasize the main point of this computation, and it is based in the fact that the infrared divergence is regularized using Mandelson-Lagrange prescription, which preserve naive power counting. That is the main property we are using. And if you use a different regularization in the infrared, you will get a different result. But you will not preserve naive power counting. So what about anomaly in more dimension and other regularizations? A 4-dimensional anomaly using Polyvillars and Mandelson-Lagrange regularization gives the standard Lorentz invariant term because of the same argument. 2-dimensional and 4-dimensional anomaly using dimensional regularization, modify accordingly to accept the gamma 5, plus Mandelson-Lagrange regularization gives the standard Lorentz invariant term. Fujikawa method plus Mandelson-Lagrange produce the standard Lorentz invariant anomaly in even dimensions. An important point of this observation for the very special relativity standard model is that this implies that cancellation of anomalies within families of quarks and leptons still holds in the Vsr standard model. That means this model is anomaly free, which is important as a test for the model. If it were anomalous, then the problem with the normalizability and unitarity will appear. So this is important for the consistency of this kind of model. As a part of this computation, one realized that the non-locality introduced in the model produce a different Schwinger-Dyson equation for the product of the current, which is important to take into account. Remember, the current are this is the vector current, this is the axial vector current. And then we consider to derive the Schwinger-Dyson equation, the path integral for the product of the current, where the action is the free action for the electron. And so the standard procedure to obtain the Schwinger-Dyson equation is to consider the local transformation, which of course when it's global is a symmetry of the action. Under this transformation, the deviation measure of the path integral is invariant. So we get the following word identity now. The derivative of the time order product of the three currents contain an extra terms. Normally, this will be 0 on the right-hand side, so you get just the identity for the triangular graph. But here there are two more terms, which correspond to the variation of the axial current under this transformation and the variation of the vector current under the same transformation. And they are non-zero because of the non-locality of the current in this case. Okay. So the non-locality of the action and current modify the word identity for the triangular graph. It's important to compute the anomaly actually, because that is why there are at least two graphs in the two-dimensional case. In the four-dimensional case are more graphs. In a similar way, we can derive the word identity for the divergence of the axial vector current. It contains extra term. So this is a peculiarity of this kind of model that we have to take into account. There is an important point to remember here, and this I just will show it in a very particular case, but it is important to recover the symmetry of the model. Then let me show you that part, which I want to comment.
Your time is up, so maybe you can go to the conclusions.
Okay, well, let me mention, you can see the screen, the screen. Wait a minute.
We see you. Oh, now
yeah. One thing before the conclusions, you can see now.
Yes.
Just before the conclusion, I want to mention that if in the Mantis and Leyland we have two null vectors, and of course that violates SIM2. That we have to devise a way to trade n bar by some other thing that will recover SIM2. The way we do it is to trade n bar using the external momentum of the graphs. Yeah. And that is important point to mention before the conclusion. So what are the conclusions? We have examined the appearance of axial anomaly in Vsr electrodynamics using polyvillars and dimensional regularization of ultraviolet divergence and Mantis and Leyland regularization of infrared divergence. Since Mantis and Leyland preserve naive power counting in loop integrals, we have shown that the usual form of the anomaly of the axial current appear without correction from Vsr terms. No anomaly is present in the vector current conservation. And we derive the word identity for the product of two vectors and one axial vector current in Vsr. The non-locality of the model introduced new contact terms. According to our result, the Vsr standard model must be free from local trial anomalies. And for more details, see this paper. Thank you.
Thank you very much for your presentation. So we still have time for one or two questions. Paul?
Thank you for this very nice talk. My question is, as you know, the discussion in even dimensions depends often whether the dimension is divisible by 4 or not divisible by 4. So I wondered if you have considered, for example, looking at the hexagon anomaly in 10 dimensions from as you did for the triangle in 4 dimensions.
Yeah, I did that using Fujikawa method. We see.
I didn't hear.
To any number of dimensions.
I would certainly expect it to happen, to work in all even dimensions, but it's not completely obvious.
Yeah, but well, the standard procedure of Fujikawa do not have any kind of restriction in that sense. I didn't do it in using perturbation theory, but I did it using the Fujikawa argument.
or Fujikawa. Yes, I really meant in perturbation theory. Yes.
Yeah. I didn't do it in perturbation theory because I was interested more in the phenomenological application for the Vsr standard model. But using Fujikawa, you can show that also in even dimensions. And I assume that also will go when you compute in perturbation theory.
Probably it does. I mean, the Fujikawa argument is rather formal, and it may hide some subtlety that you see only in perturbation theory. But I have no reason for saying that.
Okay,
Yeah, yes, indeed, but one have to check in perturbation theory. But I think it will hold. No, there is no why it's failed.
Okay, any more questions? Maybe I will ask one technological one. So you mentioned that you predict mu-3 gamma decay.
Right.
So do you have any prediction for this branching ratio?
Yeah, it is. Well, it is. Yes, I have to find the reference to that. I don't have it here, but indeed we have a prediction for that. And that prediction it is within the bound of the experimental result.
Okay, thank you very much for this talk. So let the speaker, thank that speaker again. And now we'll move to the last talk before the coffee break. So we'll have Young-Duk Kim talking about double beta decay experiment, focusing on Anomaly experiment.
Yes, it's right.
Okay, sharing is on, so please start.
Okay, thank you. Thank you for inviting me to this conference, and I really enjoyed staying here and discussing many theoretical physicists. I'm doing experiment in Korea, so my name is Young-Duk Kim, and I'm in the Center for Underground Physics of Institute for Basic Science (IBS) in Korea. I'll talk about the beta decay experiment. Basically, I will talk about the some motivation for the neutrino beta decay, and I will not really completely review the current status of the experiment, but just a little bit. I will talk about current status and comparison between the experiment and especially for what we expect for near future, not very far future. Far future is very uncertain, and I will, especially for the status for the Anomaly experiment, which is one of the example for the near future experiment. So as we all know, we have all 3 neutrino mixing and the mass differences are measured. So this is basic knowledge we are having now for these parameters are for the normal ordering for the 3 neutrinos. We have still 2 possibilities are very relevant to the experimental aspect. Whether we have a normal ordering or inverted ordering is very important. Also, we have a CP phase, and also if it's Majorana, we have 2 more Majorana phases relevant parameter. And so for the experimental neutrino mass relevant experiments are whether we have this can decide the ordering, what we have in the mass limits from the single beta decays, also the whether we have a Majorana neutrinos or Dirac neutrinos. Also, the beta decay have a limit, but also you can give only limit for the when if it's only Majorana, but still very actively pursued. This is my subject today. Neutrino mass from cosmological objects. So you all know discussed actually in this conference too, whether we have also the strand neutrinos. Those are relevant to the beta decay. For the last in 2020, there was a little bit unexpected result from the many NOVA and CTK experimental result. This was a fitting global fit for the 2019, and this is the global fit with the 2020. As you know, the right side is normal hierarchy, and the left side is the delta chi-square for the inverted mass hierarchy. As you know, the inverse mass hierarchy large delta chi-square, so we had about more than about 2.7 delta chi-square. That's about 2.5 sigma in 2019. But now the 2020, it's almost normal hierarchy and inverted hierarchy is also delta chi-square reduced between the experiments. So it's they said that without SK atmosphere, inverted ordering is now disfavored only with 1.6 sigma compared to 2.95 sigma in 2019. This change is driven by the long mass line experiment, CTK. So for experiment, we need to, anyway, so assuming the normal ordering for the targeting and the planning for experiments, I think they're all experiments now doing the experiments assuming normal ordering. But still at the 2021 list, actually said that if you include the cosmological constraint, including this oscillation experiment, still because the constraint for the inverted mass hierarchy, so overall still 2.7, 3.4 sigma for the normal hierarchy over inverted mass hierarchy, but then including cosmological constraint. For the motivation for the zero to decay, I think this is most promising beyond standard model physics. For the general neutrino, massive neutrinos, we need a right-hand neutrino and a very small nuclear coupling, which is maybe difficult for the experiment, the theoretical side. Majorana masses, if you include the right-handed Majorana mass term, likely, the Majorana can be the neutrino and the empty neutrino are the same particles, and no lepton number is needed for the conservation. System mechanism gives two Majorana mass states, very small and very large, which is very reproducing the experimental result. So how to test the neutrinos and Majorana particles? So you know, we are seeking this delta function in the spectrum for the continuous spectrum. Over the two neutrino spectrum, we actually zero neutrino spectrum. For the lepton number by electron 2, or only electron 2 electrons coming up, so no neutrinos coming out. Then the neutrino emission absorption, the exchange need a helix matching condition, which is proportional to the mass square of the neutrino mass. So this is the already 1939, just after the Thor's Majorana theory, just occurred the theory already suggested to such zero neutrino double decay to confirm neutrinos are Majorana. So that's already 80 years ago. We are still seeking this possibility for the Majorana neutrino for last 80 years without the success yet, but we are still working very hard. More quantitatively, for tens of years ago, this is formula is derived for the light neutrino exchange model, standard Majorana model for the inverse of the general neutrino double decay half-life is proportional to the square of effective neutrino mass. That effective neutrino mass is function of the mixing the phases, also the mixing angles, and also M1, M2, M3, the value itself. So this is the derived formula for the zero neutrino double decay half-life. So this is theoretically well established for this special model, but there's a lot of mechanism to make zero neutrino double decay, but this is standard model we want to stick. I don't want to discuss any other mechanism, just I will stick to this one, but from the experiment point of view. So if we discover the zero neutrino double decay, it will give effective neutrino mass, double decay neutrino mass, which is a function of this one. So theoretically, this is well calculable. It's easy to calculate. So from all the known parameters, So we don't know the actually M1 number from some constraint, but still M1 can be 0 to some number. For this effective neutron mass is a function of minimum of the lightest neutron mass, but still we don't know the mixing angle is not precisely known. So there's uncertain mixing angle. Also, we don't know any Majorana phases. So those are confined variable, just the free parameters. Then we can have the effective neutron mass as a function of neutron. So we have two different scenarios for the inverse ordering and normal ordering. But this is uncertainty we have from the current known parameters. Phases we don't know. So there's a interference between phases, and even for the quite high light mass, effective neutron mass may be 0. So we cannot really do the experiment, experimentally discover in these cases. So current mass limit for the cosmology, or for the 3 neutrino sum numbers is given by cosmology. So this cosmology limit about 120 milli-electron volt. It's very, I think it's 2 sigma, 95% confidence level of this number. But if it's 1 sigma, it's below 100 milli-electron volt. 3 sigma is a larger number. So if this is currently actually the best in terms of the constraint, cosmological number is the most severe, because that's a little bit below the Kamran-Jen, which is shown here, 60 to 160 milli-electron volt. Cutting single beta decay is 0.8 electron volt now, but they aim soon 0.2 electron volt. But another project 8, they go to below 40 milli-electron volt, maybe 40 electron volt. Something. That if it's 40 electron volt, actually it will disprove the inverted mass hierarchy. So that will be very severe, but experimentally proposed, but we really don't know how long it really takes to going to from here 800 milli-electron volt to 40 milli-electron volt. That will be really, I guess it takes a long time for the single beta decay to reach sensitive mass region. So this is one of the this Junkow's expectations. He just actually played with the numbers. So if he didn't even draw the inverted cases, this is just normal ordering cases. Normal ordering cases, if you below about the this is a 10 milli-electron volt, so about 1 milli-electron volt, a little bit over than 2 milli-electron volt. Then it will be, you can really differentiate the phases of the Majorana. So this is Majorana phases, how you can study below this interference level. You can, if you discover that number, you can really discuss the Majorana phases can be decided at this level. So this is really ultimate, maybe dreaming goal for the Majorana. If after we discover the Majorana, that's at this mass region, we can really study the Majorana phase. Decide. Another aspect of the general tablet case is stellar neutron. If stellar neutron, it will be larger probability for the zero tablet case. So this is a function of stellar neutrinos as a mixing between the electron and stellar neutrinos. Actually, this plot shows the this is the actual zero tablet, but this is only for the Majorana neutron cases. So of course, zero neutron cases you cannot apply this from constraint from the zero tablet lifetime. Even this shows the NEOS. This is NEOS is actually our experiment. We have run short baseline experiment gives electron volt stellar neutrinos, but there's also you can consider here the stellar neutrino mixing parameters can be even compared with the WRTK experiment too. This is interesting, but if you need, seems like for the, actually in my cases, we need actually it is more severe than the direct beta decay limits. Beta decay limits are here. This is actually the experiment program to also improve the from the Katrin, Tristan, improve this limit 10 to the minus 8 or 10 to the minus even 9 level for the that's a quite near future is expected. In summary, the general tablet will confirm neutrons are Majorana particles and the Lepton number conservation. non-conservation to support the system model and the leptogenesis I talked about, but this is very important, but I didn't cover this one. So now let me a little bit go to the experimental side, what we expect for the near future. This is the Engel's famous paper about the nuclear physics. This is a matrix element what need to calculate the general diameter decay half-life. So this is his expected this is expectation from the calculations for many different isotopes. The lowest one is better. Of course, the lower lifetime is easier to detect. So this is the molybdenum 100 here. One of the lowest expected half-life of general diameter decay is about 10 to the 29, but millielectron scale should be multiplied. Neon 150 is the neodymium is lower, but this is has a difficulty in the experiment. So, which isotope is best for the experiment is one of our really experimentalist side. It's the most important question we always ask ourselves: why do you do this experiment? Why do that experiment? And then actually, I was interested in because all Nutritional diameter decay is already measured and all decided very high accuracy. So this is the lifetime already measured, experimentally confirmed, all confirmed almost without error bar in this scale. This is log scale from 10 to the 19 years, 10 to 21 years, very long, up to 10 to 22 years. This is the confirmed one, but this y-axis is just theoretically the angles. This number is y-axis for each isotope. So I just draw the correlations. So this is simple to draw. I didn't really see the other people. I just drew myself. And I showed this one to Professor Ejiri. He's a very famous nuclear physicist. So he thought this is interesting. Anyway, there seems to be some correlation, weak correlation. This is about one order, less than one order. This is more than two orders. Of course, this matrix element has less dependence on the zero neutral gravity. Two neutral gravity has much strong dependence on the. So anyway, but this seems to be there's another exceptions. This I think he said this is understood. But anyway, zirconium looks like strange. But anyway, this is one tendency I can see from the two neutral and the zero neutral gravity. So basically, this is expected 10 to 27, 28 years for that. Some, of course, we need a neutron mass. So now, how sensitive to the general diameter experiments? This is a schematic for the of the experiment data. Two neutrons are always there, and general neutron is the endpoint. We need a signal. So the backgrounds are always there. So background is finite. We have a sensitivity. Experimental sensitivity is the square root of the MT. MT is mass and the time. How long you take? We call this exposure. Square root of exposure is one parameter for the finite background. For the zero background, almost zero background in the region of interest where signal expected. That if it's almost zero, zero means about less than one counts in whole energy region, whole experimental data. Then the sensitivity is proportional to the exposure. So this is the exposure versus sensitivity for the experiment sensitivity of general diameter decay. If it's very small backgrounds, it's just linear. If you have larger backgrounds, sensitivity gets worse. This is a nightmare for the experiment. So you have to run 10 years more if you just have the for 3 years. This is nightmare for the higher backgrounds. And so this is Elliott 2022 paper. It's called diameter decay Moore's law. This mass limit for the neutron mass gets improved lower and lower. This is about 1 electron volt. Now you have less than one, but at that time, about 2000, about a few hundred milli-electron volt was the limit. So germanium 76 experiment. Also tellurium. So now after 2000 years, now what will happen and what will happen? That's what I want to show. So future experiment right now they're running the one famous experiment, the Kamran-Zen. This is now gave best limit for the neutrino mass. This is running now, and their expectation is 5 times 26 years. This is currently 800 kilogram one. This is also just about to run less than 200 kilogram. This is germanium 76 data, and they all both experiment will have updated plan, but not really near future. So this will be how much we expect from this experiment. I will show. More further ambitious experiments are called Cupid in Europe, in Italy, and that's similar to our experiment Amore. So I will basically explain Amore, but basically Cupid is also more ambitious experiment, about 250 kilogram of enriched molybdenum. This is a very large experiment, upgrade of the current core experiment. This is a xenon experiment. Both are xenon experiments, also quite ambitious. Takes a little bit, or I guess it's a longer time. So what I want to show is this is another some comparison with the exposure. As I said, the mass times how long we take data versus the backgrounds. So this is a lower backgrounds, higher exposure. This is the right way to go, and most most experiments are going this direction. And currently, this is already finished. The currently running experiment. Future experiments are here. So that's what we are doing. But for the near future, this is one expected about 10 to 27 year. This kind of experiment, Amore, Cupid, Kamran-Zen, and other experiments. I will show a little bit to one. So after the 2000 years, the Engels, the Moore's law, what exponentially increased. This is still same. It was about several hundred million electron volt. This is one electron volt. This is 100 million electron volt. Now, the best one is the Xenon 136, but still, most of them actually quite follows as a function of a year. This is near future 2030, from 10 years from now. So this is the current experiment for the molybdenum 100 and the selenium 82. And this is the black one is a germanium. This is Golda, and now they may run the less than 200. This is so this is the expected. I think they are running from this year. So this is very much expected from their. So this is kind of personal, my personal judgment, but very close to their expectations. So this is almost we expect that this year results will come out with about this sensitivity. Of course, they can see the signal at this the mass, but this is really their expectations. So for molybdenum 100, this is our Amore experiment expectations at this year. So that I will. This is a very abrupt change because right now only the small experiments are running. So this is our Amore detector. So Amore detector is a molybdenum 100. We are crystals. We run some sensors. So for the double decay, so crystal temperature increase, magnetization also decrease in the attached sensors. So that's the way we pick up the signal and measure the energy, how much temperature changes. So this is a sensor is attached to here. So we have a superconductor, and the persistent current in superconductor makes B field, and that B field makes a magnetization, and temperature changes the magnetization. That's how we measure the signal. In real detector, like here, in real detector we have another scintillation light, not like a core. So we can separate the alpha signal and the beta signals by this two-way reading up. So phases now we are running Amore 1 at the Yang Lab in Korea. We are preparing Amore 2 right now. So that's the expectations what I shown. Sensitivity is 8 times 26 years, and the sensitivity the mass is 13 to 25 milli-electron volt. So that's we are running. Amore 1 is now running, so we can separate from the alpha background. Current Core experiment cannot separate these two particles, and this Q value here, this expected, we can separate the alpha and the betas. So currently, more crystals tested. Good energy resolution was obtained with a larger signal. So we want to go to a little bit larger signal, larger crystals to reduce the channels. This is something that's going on. And as I said, the background is most important. So this is the background we expect from all the measurement and simulations. It's about 2 times 10 to CKKY is a count per kb kilogram here. The kind of unit we are using for the WRTK. So this is the goal, and so this is what we measured up to now. So this is discovery sensitivity with that background. So the 5-year running Anomaly 2, we will have 4 times 10 to the 26 years with 3 sigma confidence level. So that was the one I showed in the near future. So this new experimental site is made, and the Anomaly room is prepared. This is a feature for the what we are just making the detector rooms, and this will be finished until next June. And this millikelvin temperature TR is delivered. So future, it should be more clear when we have the first data for Anomaly 2 experiment. We are just preparing now with the 90 crystals. After that, we will run 200 kilogram of crystals, 100 kilogram of molybdenum 100. That will be the largest molybdenum experiment from 2024 with the full scales. So that's the we have some discussion with the European group, and together for the molybdenum 100 low temperature cryogenic experiment. There's so summary. So that will be one of the best probe for the PSM physics experiment. We reach IO region around 2030 with not only Anomaly, the other experiment will reach IO region, not completely ruled out, but we continue to lower the sensitivities. Anomaly is aim to be close to 10 to 27 years, about 20 milli-electron volt. Installed by 2022 starting, and within several years, we will try to get to some experiments. Other experiments are actively pursued. And so there should be pursued for multiple isotopes, because we really a lot of uncertainty in the nuclear matrix elements. Also, after discovery, you need multiple isotopes to separate the mechanisms and to understand better. And so it can be discovered at any time with I think the new sensitivity below the current constraint, cosmology and the cosmology and the single beta decay. Single beta is very high, but within just below that, so still it's any time discovery is expected. Of course, if it's a random case. Thank you.
Much for this interesting talk. Are there any questions? Comments? So maybe Paul first.
This is a very nice talk. And my question is about slide number 9.
Yeah. Okay.
The question is a simple one. How much of the uncertainties in that plot are due to the uncertainties in the nuclear matrix element?
So this is this has just it has nothing to do with the matrix element. This is just this formula itself. This is effective mass, WRTK mass. Effective mass depends on the mixing angles and masses. And this is the drawn here. Effective neutral mass as a function of M1. After that, the matrix elements are entering here. Matrix elements entering here between this one and the half-life of half-life. So with the same, this is just already all decided. Of course, the one phase and the M1 is not known.
It's not displayed in that.
So this has nothing to do with the matrix element. Matrix element. It has nothing to do with the nuclear. This is just particle physics. Has no nuclear physics involved here. This one.
Thank you.
So here's another question, and no, I think you were first. Please.
Yeah, thanks for the talk. I have a question regarding slide 21, if I remember correctly. Yeah, How you can explain the value you gave for your experiment in green? Just
this one.
Yeah, this one. How this is much better than the other? It depends on nuclear matrix, or I don't know.
Right. So the nuclear matrix is one factor. For the molybdenum 100, the nuclear matrix is a large one. As angles. So this is basically for the same neutrino mass, lifetime is the shortest for the molybdenum, except this one. And so the dependence was not very large, small dependence, but still xenon is expected for same neutrino mass. Expected lifetime is longer. And so experimental-wise, we have 10 to the 27 years expected for the Anomaly or Cupid. Then it will have, with the same lifetime, Cupid or molybdenum has a better mass limit because of the trace element is really large.
Reach that value, which half-life you?
This is 27, 8 times 10 to 26 years.
Okay.
That's 13. So this was drawn. This was drawn. That plot 13 to 25 was this one. 13 to 25. That's the number what we expect. So for this one is the level of 200. This is the Kamlan Zen. So they are right now. So 5 years. That's a number they gave this one, and this is the this is tellurium. This is the core they're running now. They have given 1.5 years data. No, this is 5 years data. But certainly, most of them are expected. I guess this can be even could be discovered. Still, it's not experimentally possible. It's not constrained. This reason.
Okay, one more question.
I was wondering, what's the future potential of these detectors to rule out the inverted Mason? Is it already ruled out, or
No, it's not ruled out. Of course, it's not ruled out at all. But Mesarki is not ruled out. Still, it's possible. Even cosmology constraint is heavy, most serious. Kamlan Zen is here, so Kamlan Zen is not ruled out. This is still possible.
I see. Okay.
Parameterism.
But I think there are many other detectors, like apart from this Kamlan Zen, like
Kamlan Zen, this one I just said. This is the Kamlan Zen next release. So from 20, this is I should throw actually mass. Inverted mass hierarchy is around here, 20 to 40, comes here. So
I see. Okay.
To completely rule out, we need a little bit better than this one actually, but it's close to there. Yeah, in 2030.
Okay, so I think it's time to go for a coffee break. So let's thank the speaker again and all the speakers of the sessions. And we are back at 6:30.